Okay, let's see how far we get. This is like a review slide. So one of the things about gases, I'll draw my little box. I don't have like little props here for you. I have a few videos to show you. Hopefully they'll work. But to me, if you can picture a gas, a lot of this will make sense what gases do. To describe a gas, we need to describe the pressure. Those particles are hitting against its container. We need to describe the temperature that those particles are hanging out at. We need to describe the volume of the container that's containing the gas particles. And then we need to describe how many moles of gas particles there are. Okay, P, V, or PT, V, and N, something like that. So pressure, we talked about this the other day, and I told you that actually atmospheres are great pressure, millimeters of mercury are great pressure. This is the PSI, pounds per square inch sort of thing. You'd be able to go back and forth between atmospheres and millimeters of mercury. You will run into the unit of a torr in your lab, and 1 torr is equal to exactly 1 millimeter of mercury. So the whole millimeters of mercury, of course Hg is the symbol for the element mercury. How did that come about? Well, actually there is a way to measure the pressure of the gas particles in the atmosphere using this liquid mercury barometer is what it's called. And so the way it works is you have a glass tube. Here's our glass tube, and it's closed at one end. And basically, the way I think of it, as you kind of fill it with mercury, and then, so it's closed here, you fill it with mercury, you put your finger on it, and then you put it in the pan of mercury and pull your finger out, and they just kind of let it set. Okay? Depending upon the pressure of the gas particles in the atmosphere, it will actually create a pressure on that open pan of mercury, okay? And it will be compensated by how far up the liquid mercury goes in the glass column. So the more the pressure of the gas particles in the atmosphere, the farther up that goes in the column. Okay, have you ever heard, like, if you're into weather at all, they'll say, well, the pressure is falling. Okay, literally, the gas particles in the atmosphere have less pressure for whatever reason, and it kind of brings us different weather events. Okay, yeah, I think that is so cool. It's a mercury barometer, liquid mercury barometer, kind of messy. So these are all talking about a liquid mercury barometer, but now notice this first one is kind of silly because it's not closed at the top. Okay, it's kind of a silly sort of barometer. These next two are full-fledged liquid mercury barometers. They are closed at the top. And notice that even if it has extra room to go up, the liquid mercury will only go up in the column the same amount relative to the pressure that's being exerted on the pan underneath it. Okay? And then this one kind of makes me laugh too. It didn't make it long enough. You're like, I just think that is so funny. Right? Okay. This is another way to use liquid mercury. I'm trying to think. I don't think I use something kind of like this in organic chemistry, but if you have a gas in the flask over there at the right, okay, notice that kind of like when you guys used your burettes, you had stopcocks. There's a stopcock on that glassware over there on the right. So it's open. So right now you have gas over there, and it's open to basically leave the container and fill that kind of little neck there. So now that gray, that silver stuff right here, this is liquid mercury. Okay. In this case, basically, the pressure that's being exerted by the gas is equal to the pressure of the atmosphere. That VAR is the pressure of the atmosphere, barometric pressure. Okay, they're equal. Well, let's just say for whatever reason, your gas particles in that flask create more of a pressure. What's going to happen then is that liquid mercury is going to kind of sloop down, okay, relative to the pressure, the excess pressure it has compared to the pressure of the atmosphere, okay? Well, of course, we use the symbol delta for change in, so you can see actually the difference in pressure between the atmosphere and the pressure of the gas is there. So actually, we can use a nice little relationship here. The pressure of the gas being exerted, since the mercury is going this way, is equal to pressure of the atmosphere or barometric pressure plus delta P. We could also see a situation where the gas particles in the flask are exerting less of a pressure than the atmosphere. In this case, then actually you see your silver, your liquid silver, your liquid mercury go loop that way. Okay, and your delta P then would be, it would be negative, and we could still apply it to the barometric pressure that it would be. So that's just kind of a look at that. Okay, so now we're going to kind of walk through those 4 variables. Remember, if you have gas particles that are confined in a box, the 4 things you need to describe that gas particles are, I usually go in this order: pressure, volume, PV, and T. That's usually what I say: pressure, volume, number of moles, and temperature. So if we look at only the pressure and temperature, so this would be holding what? The volume and number of moles the same, pressure and temperature. Okay, I usually say, what happens to pressure if you change the temperature? So for instance, if you have a balloon and you heat up the particles, they're going to go faster, and it's going to create more of a pressure. Okay, we actually say then pressure, or temperature and pressure and temperature are directly proportional. And now instead of an equal sign, okay, I don't think we've talked about proportionality symbols maybe. It looks like an infinity with a bite taken out of it. Okay, it just means that they are related, proportional. As one goes up, the other one goes up. And I've got little videos for these. So now let's take another couple of variables. And so now we have, you don't want to confound your experiment. So if we're looking at this case with pressure and N is number of moles, we want to hold the volume and the temperature the same. Okay, so this makes sense. To me, I always think of blowing up a balloon. Like as you blow up a balloon, I guess you're changing the volume. But let's just say your latex gets at the end. Okay, your balloon can't get any larger. You're adding more gas particles as you inflate your balloon. The pressure increases. Makes sense, right? As one goes up, the other one goes up. They are directly proportional again. I want to think about is volume and pressure. So let's do it this way. Let's kind of change the volume and think what happens to the pressure as you change the volume. So if you have a flimsy balloon, okay, and you're not going to change the gas particles in it, that would be changing N, and you're not going to change the temperature, okay, but let's just say you take the volume and you make the volume smaller. Okay, as you make the volume smaller, the pressure is going to go up. So as your volume goes down, your pressure goes up. So this is something different than we talked about before. This is actually what we say an inverse. They're inversely proportional or inversely related. Okay, as one goes up, they're directly related. Okay, as one goes up, the other goes down. They're inversely related. So we can show an inverse relationship by using the proportionality symbol. There's infinity with the bite taken out of it. We say that volume is directly proportional to 1 over pressure. Okay, it's showing the inverse relationship. As one goes up, the other goes down. And here's a little video for that one. Okay, so this might be an extra slide, but just to kind of recap, okay, we said that pressure was directly proportional to temperature. We said that pressure was directly proportional to the number of moles, N. We said that pressure actually is inversely proportional to volume. All right. So there are these 3 guys that have these famous gas laws about them. We're going to talk about Boyle's law, Charles' law, Avogadro's law. And in each case, they take 2 variables, just like we did, and basically make a law out of it. Okay. So Boyle's law relates volume and pressure, just like we saw before. So volume is proportional to 1 over pressure. In other words, volume is inversely proportional to pressure. Charles' law looks at temperature and volume. We didn't look at this one earlier, but we'll look at it here in a minute. So according to Charles' law, volume is proportional to temperature. And Avogadro's law looks at, not so surprising, particles. So Avogadro's law looks at volume and number of moles. So volume is directly proportional to number of moles. So let's look at each one of those in a minute. So we're leading up to this one equation that actually has all four of those variables in it. And the name of the equation is called the ideal gas law equation. It's not just the gas law equation. It's the ideal gas law equation. So what does the ideal part have to do with the ideal gas law equation? Well, we are assuming that the gas particles are behaving ideally. And if they're behaving ideally, these two criteria are what works for them. Basically, there are no intermolecular forces. I'm not going to draw my little box again. I could draw my little box again. Okay? But when I draw my little box, I draw those particles far away from each other. Okay? Gases are basically, there's no intermolecular bonds. There's no intermolecular bonds between them. They're all independent. Okay? The other thing is that that ideal gas law requires is that the size, literally the size of the particle is negligible relative to the size of the container it's bumping around in. Okay? We'll talk more about non-ideal behavior coming up. Okay? Oh, I see a face back there. But look at this. See, here's the deal. We'll talk more about non-ideal behavior. But what if, here's my normal box, okay? And here's my particles, happy little particles. What if I make my box really pretty small, but I have the same number of particles in there? Okay. Actually, what I've just done is I have basically what I guess you probably would say high pressure. Okay. With this sort of situation, ideal behavior kind of goes out the door. Those particles might be close enough to actually interact with each other. You might have some intermolecular bonds even between gas particles. That's one way actually pressurizing gases that we get them to liquefy. The other thing is the volume of the gas particles, it might be significant compared to the volume of the container they're bouncing around in. So in general, at high pressures like that, non-ideal behavior goes out the door. So that's kind of, I don't know if that kind of helps classify or kind of helps clarify. So let's take a look at those gas laws, right? Boyle's law says that volume and pressure are inversely proportional to each other. Now, I want to introduce something. The thing about the proportionality symbol is, this is the way I learned it. I think it works pretty good. You can replace it with an equal sign if you introduce a constant, and we're going to do that. So here we go. Volume is equal to some constant K times 1 over P. We can do that. And actually, we can rewrite that. If we want to get P, if we want to get K by itself, what would we do? Multiply both sides by P, right? So here we go. P and P. Then those P's cancel out. We can say PV is equal to K. Are we good with that? The problem with kind of the ideal gas law equation and doing gas law problems is algebra, quite frankly. Gets me too. Like, I should have divided, you know. Okay, so we good with that? Oops, sorry. So again, all I've done here, and we're going to do this for Charles' law and for Avogadro's law, is I've replaced the proportionality symbol with an equal sign, introduced some constant K. There are a lot of constants in this universe. I love it. Oh my gosh. I like to dream of other universes where the constants actually have different values. You know, I'm just like, anyway, maybe it's just me.
Mercury is a solid.
Well, yeah, I don't know. Just other, you know, think extravagant. All right, so here's a figure that goes along with Boyle's law. Volume and pressure are inversely related. So in this little, one way that we can get to gauge pressure is, how do I say this? Do you guys see the little tan stuff? This is the gas of interest. See this is the gas of interest right here, okay? This actually is a piston that can move up and down. It's free floating, it's free moving. So in the next figure up here, I'm going to put 2 weights instead of just 1 weight. 2 weights instead of 1 weight. It should shrink down, right? All right. So if it shrinks down, we have a smaller volume, greater pressure. I like it. And notice, like it's the little things, but can you see like the density of the color increased? Okay. So V2 is smaller than V1. Okay. The pressure in the P2 actually is greater than P1. And we talked about actually pressure is force divided by area. You have the same area but more force up there with the 2 weights. So anyway, this is plotting those 2 points. Your tire pumps, right? Just your manual tire pumps. So when you go ahead and slide the handle down into the barrel, you're actually squishing that air, okay? You're decreasing the volume, you're increasing the pressure so it can go in your tire. But, you know, little things like that. Could you make a tire pump? I couldn't make a tire pump, you know? I could just barely use one. Well, I just think that is so cool. Oh, we got some other ones, okay. So, actually nothing's happening here. This is looks like an Erlenmeyer flask. It's got a sidearm, and actually it's what we call thick-walled Erlenmeyer flask because you can pressurize it, because the sidearm is there so you can draw vacuum or create pressure. So the gas of interest on these little figures, I get so excited, I love gases. The gas of interest, can you see the plunger stops right here? Okay, so the gas of interest is right here. And of course, all that's doing is making so the gas is confined. All right. So, what if, and I can go back and forth if you want to. So now look at this plunger. It used to be up here, and now it's down here. If you read the caption, all they're doing basically is taking their tire pump and basically increasing the pressure in here, which actually makes the plunger go down, okay? So here we have a decreased volume, increased pressure. That's all it is. And I think I have one more. So that's at like 2 units down. Okay, that's even farther down. Okay. Isn't that cool? So that's the gas of interest. And then we switch gears and we go to marshmallows. Okay. So this is just marshmallows minding their own business, right? And so we're going to, I think first thing we're going to do, oh, they blew up. So instead of having a tire pump like that, basically we drew a vacuum and created a low pressure in there, okay? So lower the pressure in that chamber, lower the pressure, increase the volume. Is that not cool or what? Marshmallows, gotta love them. Well, the next one, those marshmallows that are minding their own business, they switch from a vacuum to a tire pump. So there you go. They had fun doing this, I'm sure. All right. So, and this increased pressure, decreased volume. All right. So here's a few little slides that kind of show you the gas of interest is right here in the syringe again. This is the gas of interest. And what's going to happen is on the next slide, we're going to add shot, basically, to weight that down more and more. Okay, so we're going to weight that down more and more. We're going to decrease, that's going to be increasing the pressure, decreasing the volume. So now they kind of got smart. They basically said that pressure is a function of the mass that you have up there, the mass of the lead that you're looking at. That's related to pressure. And instead of plotting pressure versus volume, they are plotting pressure versus 1 over volume, because pressure is directly proportional to 1 over volume. Okay, so here's what this looks like. All right, with no shot, there you go. So again, I was looking at this in my office, I'm like, now where did that number come from? But here's the volume, okay? If you take 1 divided by 14.3, you get 0.075. Okay? They added 500 grams of shot, and now their volume decreased. okay, etc. Okay, so increasing pressure, okay, decreases volume, or you could say increasing pressure increases 1 over volume, which totally works. All right, so that was Boyle's. This is Charles. I like Charles' law too. Okay, Charles' law looks at volume and temperature. And this kind of makes sense. Did we ever look at volume and temperature? So basically, if you have a balloon and you heat it up, okay, it's basically those little particles can go faster and faster and faster, and you can actually feel your balloon getting more and more taut, like tighter. Okay, the pressure increases. So you increase temperature. Let's do that one. Increase temperature, increase volume. That's a good example of that. Well, this is assuming your pressure, number of moles are going to stay constant. I don't have a good example. They're going to use liquid nitrogen in a photo coming up. That's a good example. So let's go ahead and replace the proportionality symbol with an equal sign. And then we have to insert a constant. So volume is equal to KT. If we want to get the constant by itself, then we would say volume divided by temperature is equal to some constant K. All right. So now on to the example. Or a couple examples, I guess. Okay, so left and right, we have the scenario 1 and scenario 2. Scenario 1 looks a little darker, right? Okay, scenario 2 looks a little lighter. Okay, notice they have the movable piston. In this case, we have the same weight on both of them, same pressure on both of them. Pressure remains constant, the volume changes. The one over there on your right is hotter. Okay, basically all we've done between those two is heat them up. So we actually could plot them. What volume is contained in one? It's right here, 20 milliliters for one. What volume is contained in two? It's over here, 40 milliliters in container 2. Okay, what are their temperatures? Well, we can pick that off too. I don't know. This looks like, really? That's pretty darn cold. Let's see, this is like negative 80 degrees Celsius. Wow. And this one looks like it's maybe 120 or so degrees Celsius. Okay, so you increase the temperature, it increases the volume, assuming you want to have the same pressure as indicated. Now, here's where I need to introduce something important. So along the temperature scale here, these are in degrees Celsius. Whenever you work gas law problems, your temperature always has to be not in degrees Celsius, but in units of Kelvin. Always, always, always. When you work thermodynamic problems, who cares? Because the change is the same on both scales, Celsius and Kelvin. But when you work gas law problems, your temperatures always have to be in units of Kelvin. And here's kind of why. A very cool, no pun intended, thing happens when you take a gas and you lower the temperature, you lower the temperature, you lower the temperature. So we're like, we know, according to Charles' law, that if you take a gas and you leave it the same pressure, same number of moles, that as you reduce the temperature, you're going to reduce the volume. Reduce the temperature, you reduce the volume. Da, 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 da. Well, if you go back to, remember absolute zero? There's absolute zero right there. Absolute zero. What volume does a gas have at absolute zero? 0. It hurts my brain to think about it too. The problem, quite frankly, is you see the dot, dot, dots right here. This experiment really doesn't work very well because as you cool it down, basically it becomes closer, particles become closer and closer together, which begins to violate one of the ideal gas law behaviors, which is that they have no interaction with each other. If they're close together, slow enough, they can have interaction with each other. Okay, but anyway, always use units of Kelvin for temperature. It's absolutely imperative. And unfortunately, but you guys will do fine with it. A lot of times, the problems that you find for gas law problems will give the temperature in degrees Celsius, and you just have to convert it. Yes. Oh, let's remember how we do that. Let's remember together. If I can remember, if you can remember. Okay, if you have the degrees Celsius temperature, you get the Kelvin by adding 273.15. Okay, and if you have the degrees Celsius, if you have the Kelvin, you can subtract 273.15 to go to Kelvin. So remember how to do that. And the reason this works is because actually the units are the same, they're just offset. Okay, cool. So here's a little video for volume and temperature. All right. Okay. This was the one I was talking about with liquid nitrogen. So this is related to temperature and volume. The gas of interest is in the balloons. So they're going to take those balloons minding their own business, and they're going to stick them in that cold liquid nitrogen. Okay, so you cool your gas down, you lower the temperature, you lower the volume. Okay, and so they're all shriveled up in there. Is that not adorable? And then the last thing they do is they take them back out again. And it's kind of like when you get ants in the mail, like they're like cold and stuff, and then you reanimate them as they warm up. Gas particles are like that. So you increase the temperature, you increase the volume again. I just think it's cool when you look at them all shrunk down like that, the same gas particles are in them there that is in them in there. I don't know. Okay, Avogadro's law. Avogadro's law links number of moles of gas particles and the volume. This is assuming that the pressure remains constant and the temperature remains constant. So again, we can replace the proportionality symbol with an equal sign, introduce a K, and then go ahead and get the K by itself, and we have volume over number of moles is constant. Volume over number of moles is equal to some constant. It's always constant, assuming that your pressure and temperature is not changing. Okay, Avogadro's law. So this actually has a neat consequence when it comes to stoichiometry and reactions involving only gases. So the reaction I want to look at is creating water. So the video you're going to see is to taking hydrogen and oxygen and making water. So all gases. When I got so excited about gases and said to describe a gas, all you need is the pressure, the volume, the number of moles, and the temperature. You don't care what the identity of the gas particles are. They will all behave the same. So Avogadro's law says that 8 molecules of hydrogen will have the same volume as 8 molecules of water. N is the same. So the volumes need to be the same. Okay. So volume is related to N. Volume is related to the number of moles. Stoichiometry relates the number of moles that are reacting to. So the video we saw did this chemical reaction, where you guys could come up with a set of stoichiometric coefficients to balance it. You would say that 2 moles of hydrogen molecules react with 1 mole of oxygen molecules to form 2 moles of water molecules. Notice the little g, they're all in their gaseous state. You guys have this one? Oh, whoa, okay. They're all in their gaseous state. Maybe I introduce this just to kind of clarify it for my own. Okay.
Oh, we have that though.
You have this one?
Yeah, we have that. We
Oh.
just don't have the thing at the top.
Oh, okay. All
Write
right.
that in.
Yeah, because it made more sense to me. So we have, what if you were to take 2 volumes of liters, 2 liters of hydrogen, how many liters of oxygen would it react with? 1 liter, exactly. And then how many liters of water, gaseous water molecules would it form? 2 liters, exactly. Now, near the end, one of the things we need to cover with gases or wrestle with gases is working with gases in stoichiometry. And actually, we're going to come back and revisit this because this can actually be an easy way to work stoichiometric calculations. Cool. All right. Let's bring it all together, shall we? So the top one is Boyle's law, the next one is Charles' law, and the last one is Avogadro's law. The cool thing about all of these is we have talked about how volume relates to first pressure, then temperature, and the number of moles. We can actually bring them together. Doesn't look like we can bring them together. And we can make a joint proportionality, say volume is equal to, and then combine the other things on the other side. Not equal to, I should say proportional to. We could say volume is proportional to number of moles times the temperature divided by the pressure. So all I've done is basically kind of combine these. All of these ended up right there. Well, you know what we can do if we want to go ahead and get rid of our proportionality symbol. We can replace it with an equal sign, which is what we're going to do, as long as we introduce a constant. And that's exactly what comes next. Okay, so we can say the volume is equal to now some constant K times the number of moles times the temperature divided by the pressure. And that's all related to basically what we know about gases. Well, we're going to go ahead and get K by itself. And this is, like I said, I have to, every time I make an algebra, move like from there to there, I have to concentrate. So if I want to get K by itself, I multiply both sides by what? P over NT, basically, right? And there we go. And in this universe, actually, that K has a specific value, something you're going to want to memorize, something you're going to want to put on your sheet that you'd bring to your exam with you. There is actually a value for R. R, we took K and we're like, no, it's not generic. It really is what we call the ideal gas law constant, R. Okay? Pirates love it, right? But usually, to me, the ideal gas law equation doesn't look like this. I like it flattened out. So actually, this is what I'm used to seeing the ideal gas law equation as. It's nice and flat. And I think it really should be like a rock song or something, a rap song. PV is equal to nRT. Okay, so all we've done basically is combine those three guys' laws, okay, joint proportionality, and come up with how those four variables relate to some constant. And now we're not going to use K, we're actually going to call it the ideal gas law constant R. It's wonderful. And I said this is kind of like physics where you just basically plug in the and that's what it is. If you've done many gas law problems, you kind of know what I'm talking about. Okay, so PV is equal to nRT. And there are different values for R, but I would suggest you use this one, 0.082058. There is uncertainty in that, but that gives you 5 significant figures, which is quite a bit. Yeah, 0.082058. Now that is if your pressure is in units of atmospheres. And to me, I was getting ready for today's lecture and I looked online and oh my gosh, there's like a website where you can have values of R, just anything you possibly want. But if your pressure is in atmospheres, that's going to be the value. If your volume is in liters, that's the value. N, the amount, is the number of moles of gas particles, and T is in units of Kelvin. So what's really important, and we stress this clear back from the first part of the class, what's really important are units. So units of R for this value, 0.082058, are liters atmospheres per mole Kelvin. So that's very important. On your final exam, you will have some gas law problems. And it's just like the theme of this semester is always show units. You always have to show your units if you're working them out, working the problems out. All right. So let's work a problem. Okay? So I'm going to go ahead and draw my little box. I haven't drawn it for a little while. Okay. Here's my box. And the gas this happens to be is CO2. So I don't know. I don't always draw a box. But what I probably more importantly do is next to or down somewhere is I do P is equal to, V is equal to, N is equal to, T is equal to, and I remember that PV is equal to nRT. Okay, so that's what's going on in the back of my head, probably not a picture. So then I pick out from the problem what we know. It says what volume, so I guess right away, if I'm just going to kind of march through the problem, I'll find my volume, I'll put a question mark. What volume, okay, will 0.20 grams of carbon dioxide. Now, if they give you a mass of the gas, honestly, you're going to use that for N. N is equal to, and I'm just going to say from 0.20 grams CO2. How are we going to get N? Well, we're going to go from grams to moles using the molar mass of CO2. It gives the pressure is 732 millimeters mercury, direct. Note to self, that needs to be converted to atmospheres if we're going to use the ideal gas law constant that I usually use. But no worries, remember that we know that 1 atmosphere is exactly equal to 760 millimeters mercury. That's how we're going to do that conversion. But you have to show that. Temperature of, temperature of 22.0 degrees Celsius. And note to self, we're going to have to add 273.15 to get it to units of Kelvin, direct. But that's kind of what we have going on here. It's not too bad. It's just kind of, there's some front end things we need to do. Okay, so what I like to do is to rearrange the ideal gas law equation for what I'm trying to solve for. In this case, it's volume. So like I said, don't let algebra bite you in the butt. Divide both sides by P, okay? And we get volume is equal to nRT divided by P. Now, some students like to just leave it and then plug in, and then I like to rearrange it and solve for what I'm trying to find. All right, so let's kind of do some fixing on the front end. Okay, so again, the value of R we're going to use is 0.082058. I swear in my notes somewhere, and I'll have to find that. Maybe you guys can find it for me. I swear sometimes I have that value as a 7. I don't know. 0.082058 though. All right, so the point here is that actually our volume is going to be in units of liters. It just will be. And I'll show you a factor label when we plug in how everything cancels except for liters. All right, here we go. Here's the background stuff. We had 0.20 grams of CO2. We need to convert that to moles. You will need to knock out the molar mass of CO2, which, remember, we did those combustion problems? If you remember, you take 1 times the mass of carbon, 12.01, plus 2 times the mass of oxygen, 16.00. Molar mass is 44.01 grams per mole. This is like stuff you guys did earlier. And then to get moles of CO2 gas particles, we take the mass of CO2, which is 0.20 grams, times 1 mole, the molar mass, 1 mole over 0.4401 grams. And we do that so then our grams cancel. Oops. Units of grams cancel. We're left with units of moles. So that's our N. And sometimes I'll go put that back at my N. All right, what else do we need to fix? Oh, gotta fix the temperature. Now remember, since we're adding, we round according to decimals, and that Celsius temperature was 1 decimal, so honestly, we're only allowed 1 decimal in our Kelvin temperature. So 22.0 plus 273.15 rounded to 1 decimal is 295.2 Kelvin. So there's our Kelvin temperature. And then what else do we got to fix? Oh my gosh, we have to fix the pressure. So there actually is another ideal gas law constant out there that, and I swear that's what I learned in high school. I don't know. But it's in units of, instead of atmospheres, liters per mole Kelvin, it's units of millimeters mercury per liter mole Kelvin. So we take the 732 millimeters of mercury that was given and take it times 1 atmosphere over 760 millimeters of mercury. I'll just remind you what was on the slide earlier, that actually that relationship is exact. And we all know what that means. Okay, that means it brings no uncertainty. We don't round according to 2 decimals. So that's why actually we are rounding according to 3 decimals. So our pressure to plug in is 0.963 atmospheres. That works. Now we're ready to execute, finally. Oh my gosh. Okay. But remember, when you substitute in, you have to include the units. Okay? So N is 0.0045 moles. R in the numerator also is 0.082058. Units of R are liters atmospheres per mole Kelvin. And the Kelvin temperature we had was 295.2 Kelvin. And then the pressure that we got is 0.963 atmospheres. Now we're all about, it's called dimensional analysis or dimensional consistency. So do you guys buy this, that this moles cancel, Kelvins cancel, actually units of atmospheres in the numerator of the numerator cancel with units of atmospheres, just simply in the numerator of the denominator. So we have units of liters. Looks like we're only allowed 2 significant figures, even though it's tempting to give us more. So the answer would be 0.11 liters. Okay. Now I do have 3 homework assignments that will be due on Friday. Yay! So your last assignment slide is chapter 6, questions, it's multiple questions, but the ones that are due Friday are 27, 28, and 30. (27, 28, and 30). And I just want to kind of show you how these are just right along the line of what we've been doing. (27, 28, and 30). So the first one looks like this, right? Notice that, and actually in this thing I can like copy and paste, so I drew a little box each time. You wouldn't. But this is kind of the scenario. It's very similar to what we were doing. The next one looks like this. Okay. I don't think there's anything tricky here, but then again, okay. And then the next one kind of looks like this. You know. Yep, it's just kind of a different variable.
We're gonna get Kelvin, and then all we have to do is just convert back to Celsius.
Mm-hmm. And remember, you're gonna, subtract 273.15. Okay? Alrighty then. We'll see you tomorrow in the normal room.